Okay, so in this lesson we are solving integrals with U-substitution, and this is the first technique that I will discuss in these lessons. Our goal here is to find an interior function and set it equal to u. What that means is if there's a function inside of a square root or a function inside of a cubing function, that's our interior function, and we want to set that equal to u. Notice in red here I say that this is a strategy, one of many that we will learn, and it will not work in all cases. So we will explore a few different strategies, and finally, after we've discussed all of these strategies, we'll look at making choices, which technique to use for different integrals, and we'll get through that after we've seen a couple of different cases. So here with our first example, I have a direct substitution example, and that means that we won't have to make any adjustments after we find our u and our derivative of u. And you can see here that the x cubed plus 7 is our interior function, so that got set equal to u. If you take the derivative of x cubed plus 7, you get 3x squared plus 0. That is our du, and you always have to attach a dx to that to make the substitution complete. In our next slide here, I ask why is du equal to 3x squared? Just to work this out, we say that if u is equal to x cubed plus 7, then by implicit differentiation, we take d dx of u is equal to d dx of x cubed plus 7. And the derivative of u is 1, but because the variables don't match, we have to follow by a du dx. So we have 1 du dx. And on the right-hand side, the variables do match. We don't need that extra term. We would get dx over dx, which is equal to 1. And we're simply left with 3x squared. So if we continue with this, you can see that you can now multiply both sides by dx. Here they will cancel, and we're left with du equals 3x squared. Now, we don't want to, forgot my dx there. We don't want to go through this process every time. We just want to say that when u is equal to x cubed plus 7, we take the derivative of x cubed plus 7 and attach a dx to it. This justifies it. It'll follow this pattern every time. We don't need to actually show this work. So if we come back to our problem and we continue with this, we see that x cubed plus 7 is going to be replaced by the u variable, and the dx is missing here. We see that the 3x squared dx, here's our 3x squared, here's our dx, all of that we're going to trade for du. So this integral can now be expressed as u squared du, where the u is x cubed plus 7 raised to the second power, and the du replaces the 3x squared dx. Now this was what we were saying is the purpose of substitution method. It simplifies it to a problem that we know how to solve. It makes a complex problem manageable. Now we apply the power rule for integration. And we see that we get 1/3 u to the third plus c. And the one thing we want to recall is that this problem was not given to us using the u variable. It was given to us using the x variable. So now we want to replace u with the x cubed plus 7. So our final answer is 1/3 x cubed plus 7 in parentheses raised to the third power plus c. And we can check this answer by taking the derivative with the chain rule, and in doing so, we would see that we get 3x squared times x cubed plus 7 to the second power. So this is our indefinite integral. In terms of u. And when we return it back to its original variable, we call that back substitution. And to demonstrate the derivative here, we would take 3 and multiply it by the coefficient in front. So we have 3 times 1/3 x cubed plus 7 to the 3 minus 1 power. So that's the power rule for derivatives. The derivative of a constant is always 0, so the c will become 0. And this gives us 3 times 1/3 is 1. We have x cubed plus 7 to the second power. This is the outside derivative. And now we want to multiply it by the derivative of the inside. This is the chain rule. And the derivative of x cubed plus 7 is 3x squared. And we have the x cubed plus 7 to the second power. So this is the problem that we originally started with. So we showed that our answer is indeed the antiderivative to 3x squared times x cubed plus 7 to the second power by taking the derivative of our answer. So now here's a second example. In this example, again, it's direct substitution, but there's going to be some rearranging that we need to do. It's not going to be an exact fit. So if we look at this example, we say, let's look at the interior function. That will be our u. Let u equal 2x to the 5th plus pi. Then du, we said we want to just do this streamlined now. We don't want to prove it, just find the derivative and attach a dx to it. So the derivative of 2x to the 5th is 10x to the 4th. The derivative of pi, since it's a constant, is 0. And then we attach our dx. So if we look at our problem, we see that 20 can be written as 2 times 10. And then we have our x to the 4th there. And then we have our 2x to the 5th plus pi, all raised to the 3rd power dx. So we want to take the 10x to the 4th dx, 10x to the 4th dx. All of this will be replaced with du. And my interior function here will be replaced with u. So now we're just swapping things out. We still have a 2 here, so I can say this is the antiderivative of 2. The inside of the parentheses is now u, raised to the 3rd power, du. And again, U-substitution has taken a complicated integral and reduced it down to something very simple. We can apply the power rule for antiderivatives. And Now that we have our antiderivative, we can return it to its original variable. That would be replace u with 2x to the 5th plus pi. I can reduce that 2/4 to 1/2. We see that the new exponent is 4 due to the antiderivative, and then our plus c. This is our final answer. Again, if you want to check your answer, you can apply the derivative using chain rule, and it will return to you the function that was in our integral at the beginning. And here we have a third example. This one again is direct substitution, but adjustment is going to be needed to make this happen. We see that our interior function is 7x squared minus 6, so we say let u equal 7x squared minus 6. The derivative of u is 14x dx. Again, we want to just do that streamlined derivative of u. We don't want to prove it anymore. And when we look at this problem, we say, well, we're missing something for our du. Our du has a 14, an x, and a dx. Well, I see the x and the dx. It's missing the 14. And this is a very simple fix. This is why we have an adjustment. If we look at the integral, the number in front of x is 1, and we can rewrite the number 1 into infinitely many forms. In this case, we wanted to involve the number 14. So 14 over 14 is equal to the number 1. Well, I want the numerator of that 14 to stay with my x and my dx, so I can swap it out with du. And the denominator of the 14, I'm going to move out in front of the integral. So we move that out front. And then we have 14x times the square root of 7x squared minus 6 dx. And we say we haven't changed the integral, we just gave it a new form. I often use the analogy with money. I can take $1 and trade it for 4 quarters, or I can take $1 and trade it for 10 dimes. Well, here I took the number 1 and I traded it for 14 over 14 so that I can get the necessary coefficient for my du. Now we see that the 14x dx will all be replaced by du, and everything under the radical is going to be replaced by u. The 1 over 14 is still out in front. The square root of u can be written as u to the 1/2 power, and then the 14x dx is replaced by du. Now we want to take the antiderivative of this. Let's continue on another page. So now we can say that the antiderivative of u to the 1/2 is, we add 1 to 1/2, we get 3/2 in the exponent. When we divide by 3/2, that gives us 2/3 u to the 3/2 plus c. And then we have this 1 over 14 out here. Now, this is another scenario that occurs with these types of integrals. When we distribute that 1 over 14 here, we have to remember that c is an unknown constant. And if I take a constant that is unknown and multiply it by 1 over 14, it will give me another unknown constant. So we don't need to write c over 14. We can still write it just as c, because an unknown constant times a known constant is still unknown. We just leave it as a plus c. Now that we have our antiderivative, we need to return it to its form of x. So let me just look back. X is equal to 7x squared minus 6. I want to plug that back in. Once again, this is our final answer. If we want to check if this answer is correct, we can do so by taking the derivative using the chain rule.